And we're putting together all of our material on limits and continuity. First, some true false. Is it possible for the graph of a rational function to cross a vertical asymptote? No, it is not. But the next question, can it cross a horizontal asymptote? And that it can do. So, for example, you've seen rational functions perhaps that look like this. So cannot cross a vertical asymptote, but sometimes, not always, but sometimes it crosses or intersects a horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. That would be true. The domain of this function, we know our common function, our square root of x graph, is going to be moved 3 units to the right. So closed endpoint at 3, 0. So that looks like a correct domain. If f of x is continuous over a closed interval and r is an element of the open interval from p to q, then the limit must be equal to f of r. So if it is continuous, remember our theorem, continuity guarantees a limit. So if f is continuous over this interval and r is somewhere between p and q, then we can find the limit by directly substituting r into our function. So that would be true. If the limit as we approach 5 from the left side is 11 and the limit as we approach 5 from the right side is 11, then is the overall limit equal to 11? That would be our definition of a limit. Number 7, if the limit as x approaches infinity is 1, that would be the right end behavior of the graph. And the limit as x approaches negative infinity is also 1. That would be the left end behavior. Then x equals 1 is a vertical asymptote. No, I believe this is telling us that y equals 1 is a horizontal asymptote. So that would be false. If f and g are each continuous, then does the limit of their sum exist? Well, remember that a continuous function, if it's continuous over the reals, then the limit exists everywhere over the reals. And we have a property of continuity that the sum of continuous functions is also a continuous function. So that we could use our theorems to prove is true. If f and g are each continuous, then does the limit of their quotient always exist? Well, the limit of their sum would always exist, but the limit of their quotient could have a counterexample. So not when g of x is equal to 0. So it may or may not happen, but it is not 100% true. Number 10, we have a rational function. Then the limit as x approaches 0 from the small side. So we're thinking here, what if x were just slightly smaller than 0? So think of plugging a number in, but we're going to square it. So both our numerator and our denominator would be positive. So we know next to this vertical asymptote that it would be going to infinity. And question 11 says, not what happens as we're approaching the vertical asymptote, but what happens on the left end of the graph as x approaches negative infinity. We're going to square that negative number in the denominator. So as the denominator gets larger, the fraction goes to 0 on both the left and the right end of the graph. Question 12 looks like it's a question about applying our limit laws. We might have to do some thinking here. The limit as x approaches some constant a of this square root, is it equivalent to doing the limit of x first? So changing the order of operations. So can we rewrite this so that we have a similar order of operations aside from the fact that we're going to do the limit first rather than last? Well, this might take a little bit of thinking, when are these two things equal? So the square root of 3x squared minus 7 is defined for its domain. It is defined when 3x squared minus 7 is greater than or equal to 0. So you could do a little bit of algebra here to find its domain. And this would be when x is less than or equal to negative 7/3, or when x is greater than or equal to, square root of, or greater than the positive square root. So our graph of this function, let me come back and mark it here. Our graph of this, making a mess here. The graph of this function is something like our square root graph, but it has a split domain. So this would be our square root of 7/3 and our negative square root of 7/3. So what do we know about comparing it to this next function? Well, when would this be defined? Well, the limit as x goes to a of x would just be a. So this would have exactly the same domain. So when it's defined for one, it's defined for the other. So I think the fact that it says is equivalent to is true. Either they both are defined or neither is defined in the middle of the graph. Okay, back to a rational function. Has a removable discontinuity? No, when the denominator is equal to 0, x equals negative 2 is a vertical asymptote. So that would be an infinite discontinuity. So an infinite discontinuity, not a removable. So that would be a vocabulary question. That would make that false. The same function in number 14, does it have an x-intercept? Well, remember, for an x-intercept, we need y to be equal to 0. When is a fraction equal to 0? A fraction is equal to 0 when its numerator is equal to 0. So our x-intercept would be at 1, 0 rather than negative 2, 0. So that would be false. And the same function again. Does it have a horizontal asymptote at y equals negative 1/2? The degrees are equal here of the numerator and the denominator. So the ratio of our leading coefficients, our horizontal asymptote would be y equals 1. So that would also be false. All right. And let's see if I can get our graph visible within the screen capture here. As x approaches 2 from the left side, so we would be over here on this section of the highway, so we would reach a limit of 2. The limit as x approaches 2 from the right side, we would be over here, so we would be reaching a limit of 0. And does the overall limit exist? It does not, because the left and the right-hand limits do not agree. All right, how about the limit as we approach 4 from the left side? We're over here, so we would reach a y-coordinate of 3. And as we approach 4 from the right side, we're up here. We would approach that removable discontinuity. But the two left and right-hand limits agree, so the overall limit, of course, we know exists at a removable discontinuity. So we have a jump discontinuity at 2 and a removable discontinuity at 4. All right, which of these describes the behavior of this graph at x equals 0? Well, notice that if we're coming from the left towards 0, we can reach a closed endpoint. So we would say it is continuous at x equals 0 from the left side. From the right side, notice, however, we have an open endpoint. So it is discontinuous from the right side. So for closed endpoints, we can have a one-sided limit. So here it is continuous from the left, but discontinuous from the right. So choice A, I think, describes that. We could check some of the others here. Does it have a limit of -1? No, of course it has no overall limit because the left and the right-hand limits do not agree. All right, so here if we did direct substitution, we would have our 0 over 0 case, but we know that we can factor. So perhaps we can remove that common factor. So don't forget how to factor the difference of cubes. And now we've removed our 0 over 0 factor, so we can plug 3 in for x. And you maybe have seen this happen often enough here. So we'll have a 9 plus an 18. Oops. Let's go back there. Don't double that middle term. I factored that incorrectly. The middle term is the opposite of the product of the cube roots. Sorry. All right, so let's try that again. Now when we plug 3 in here, we'll have 9 plus 9 plus 9. So how I caught that was I was going to say perhaps you've seen that pattern happen in other problems, and then I had not followed the correct pattern myself. All right, here if we try direct substitution, again we have our 0 over 0 problem. So let's see if we can remove a common factor. So notice that you might find it quicker when you're doing your factoring by trial and error to look at and guess that perhaps there's a common factor. And then, of course, FOIL to check out to see that it works. And indeed, there goes our problem factor. So now we can do direct substitution, put 1 in. That problem looks familiar. I think perhaps we've done it before. And in 27, if we put -2, we would see that we have this 0 in the denominator problem. So I think we're doing some repetition on some of these problems. So to get a common denominator, I need to multiply the top and the bottom of this first fraction by x minus 2. So we need to do some simplifying first. So now our numerator here would be x minus 2 in the first fraction, and then we would have our common denominator, and you could probably skip right to the next step here. That gives us our common denominator. All right, so now when you put those numerators together, you can see that we have our x plus 2, and that was indeed the factor that was causing the 0 over 0 problem. So once we remove that factor, now we can solve our limit by direct substitution, and we'll come up with -1/4 if my arithmetic is correct. 28, we multiplied. This is a complex fraction. If we put 1 in, you can see again that we would have our 0 over 0 problem. So we simplified first. So we multiplied the numerator and the denominator. And don't forget then that we're using a distributive property. So in our numerator, the first term, the x squareds cancel. And in the second term, we have minus x squared. And we'll leave our denominator. So I'm not sure I needed to do this video. It looks like we've practiced many of these before. I wanted to factor this so that it cancels with x minus 1. So to reverse the factors, I think of it as factoring out a -1. Lots of different ways of looking at that. But now it would be positive x squared minus 1. So reverse the terms first. You're going to end up with an opposite sooner or later, whichever method of factoring you use. And now I'm ready to put a 1 in by direct substitution. So we have the opposite of 2 in our numerator and a 1 in the denominator. So I guess I could have just written -2 there. All right. The natural log of sine as x goes to pi over 2. Well, sine is a continuous function, so its limit exists everywhere. And the natural log, we know the domain of a natural log is 0 to infinity. So as long as we're within 0 to infinity, we know the natural log is also continuous. So we could do order of operations here, and we could do direct substitution. So we're going to come up with the limit. Actually, once we do direct substitution, I don't need that limit anymore. So we know that the sine of pi over 2 is 1, so the natural log of 1 is 0. And here we're going to infinity, so we're looking for the right end behavior. There is a common factor we could cancel, but the denominator will still have a greater power, so whether you factor that immediately or whether you just say for infinity, I know the denominator will have the greater power, so you can perhaps just see what's going to happen here. That even if I cancel here, the denominator still has the greater degree. So when the denominator has the greater degree, we know that our horizontal asymptote will be at y equals 0. And in 31, I see an irrational binomial. So rationalize by the conjugate. When it looks like a binomial, always go for this trick. Why I needed to do it, I should have mentioned. If you plug 2 in for the function again, you'd see that you'd have a 0 over 0 situation. So we're always using an algebra trick so that we can take care of the removable discontinuity. So now our numerator would be an x plus 2 minus a 4. And that will cancel with that first factor in the denominator. So this is indeed x minus 2, as is this, so our numerator would just be 1. And we can plug 2 in to come up with our limit. 1 in the numerator. Square root of 4 is 2 plus 2. So 1/4 is our limit. All right. Limit as x goes to negative infinity. All right. So ratio of the leading coefficients here would give us our horizontal asymptote. So positive 2 over negative 4. So our horizontal asymptote would be at y equals negative 2. If you want to check out that it's the same whether it's positive or negative infinity, you could think about putting in a negative number into both of these x squareds. They would both be negative, so they would cancel back out again. So negative 2 will be our horizontal asymptote. The left end behavior of cosine, we've used this example before. Sine and cosine waves have boundaries of 1 and negative 1, but they do not have a horizontal asymptote. So there is no limit here. The limit as x goes to infinity makes our exponents huge. So these terms become larger and larger. So these two terms eventually will become negligible. If I can spell that right, negligible. It's a hard word to spell for me. If I put infinity here, then we'll have 5 times something very large compared to 1 times that something very large. So the ratio will be 5. When x goes to negative infinity, however, that changes the game here because now our exponents will be negative. So e to a very negative exponent becomes closer and closer to 0. So now these are the two terms that are negligible. So our ratio turns out to be negative 2/7 as our limit. As x goes to infinity, here we've got the same situation. This term goes to 0, becomes negligible, in other words. So we would get closer and closer to a value of 3. And here is our theorem. The limit as of sine of a glob over the glob as the glob goes to 0. That is a theorem. We know that value is 1. And in 37, we want to use that theorem. We do not have sine of a glob over the glob, so we got to do a little bit of work. Remember that we brought the 2 out of the limit using our limit law. We cannot factor the 7 out of the sine function. That's stuck there. So we still don't have the limit of sine of a glob over the glob. We would like to have a 7 in the denominator. Well, we could do that if we put a 7 in the numerator, but we don't want to write it there. Then we would factor that 7 out in front of the limit. So we're using our identity property. And now here's our theorem. The limit as x goes to infinity is going to make this sine of a glob over the glob be equal to our theorem. So we'll have 7/2 times 1. And again, once you've seen the pattern, if you're sure you've got it, you don't have to show that work. And here we have our race to see which is growing faster, numerator or denominator. So here we have e to the x, so our base is a constant, and here we have x to the x. That's our fastest growing function here. So the denominator is growing faster, so that takes the fraction to 0. 39, is this function continuous at -2? Well, think what happens if we put -2 into that function. If we put -2, the opposite of -2 would become +2. So in fact, we know that that is the endpoint of the graph. So you can see if you put -3 in here, that you would get the square root of 1. If you put -4 in there, it's going to be the square root of 2. So do you see that we actually have a version of our square root function with this as its right endpoint? So is it continuous at -2? Well, there's a left-hand limit. We can get to the closed endpoint. There's no right-hand limit. So you could say that f is continuous from the right, oops, sorry, I guess that's the left, from the left at x equals -2. Remember that closed endpoint requires only a one-sided limit. So you don't have to write what I just did in parentheses here. Closed endpoint requires only a one-sided limit. If that had been an open endpoint, then it would be discontinuous. All right, so at a closed endpoint, can you get there from one side? Is this piecewise defined function continuous at x equals 4? Well, let's find out. The limit as x approaches 4 from the left side would have to equal the limit as x approaches 4 from, did I say that backwards again? 4 from the left side, the limit as x approaches 4 from the right side. And that cannot be a pop point. It has to be exactly equal to what we would get by direct substitution. So we want to check this out. When x is smaller than 4, we would use this x squared minus 1, but now remember that we're putting 4 in there. Is that equal to, if we put 4 in from the right side, so that would be our 2 times 4 plus 7, and is that equal to what we get by direct substitution of 4 would be that middle point of 11. So let's find out. Here we've got 15 is equal to 15 is not equal to 11. So the limit, these first two tells us that the limit exists. The limit exists, but then this point would be a pop point. So no, it is not continuous. No, it has a removable discontinuity. A hole in the graph. It has a removable discontinuity at 4, 15 with a pop point at 4, 11. All right, so you wouldn't necessarily have to be that specific. I think your work has already explained that. All right, let's see if we can match to our graph here. Looks like I kind of cut off the letter A. So we want the end behaviors, the limit on both the plus and minus infinity, to be 0. So I guess that needs a horizontal asymptote at 0. So I think we can already rule out A, D, and E. We want the left-hand limit as we approach -1. And we want the left-hand limit as we approach +1 to both go to negative infinity. So as we approach -1 from the small side, and as we approach +1 from the small side, we want the graph to be going down. So I think it can only be letter B. Here, as we're approaching -1, it's rising, so that would not work. All right, find some more limits. As x approaches -2 from the small side, I would use this part of the function. So I would plug -2 in there. And when x is -2, we'd have minus a -2 would become +2. So we'd have the square root of 0. The limit as x approaches -2 from the positive side, -2 from the positive side, we'd have to use this middle, and that would be equal to our x value. So that would be equal to -2. So our overall limit does not exist. The limit as we approach +2 from the small side, so let me switch colors here. If we approach +2 from the small side, that fits into this section of the graph. So that would go to 2. And as we approach 2 from the right side, bigger than 2, we have to use this domain. So if we substituted 2 into the function, we'd have a 4 and a 6 minus an 8, so we would have a 2. And yes, the overall limit does exist because the left and the right hand limits agree. All right, can we make this function continuous over all real numbers? So notice here that we've got this greater than or equal to. So we've got, this is a parabola, a quadratic function. So we know that polynomial functions are continuous, and this is a linear function. So we know polynomial functions are continuous over all real numbers. So this piecewise defined function is continuous everywhere except perhaps at x equals 2. So we need it to pick up where it left off. So for continuity, we need the following, the definition of continuity to exist. So we need the limit as x approaches 2 from the left side, because that's one piece of our piecewise defined function, to be equal to the limit as x approaches 2 from the right side. So if those two are equal, that gives us an overall limit, and we need that to be equal to f of 2. Well, notice that these two are the same domain. These two are both included in the second part of the domain. So both of these would be equal to 2 times c minus, and now don't put in x, we're looking specifically when x is equal to 2. And when x is smaller than 2, we are using c squared minus our x value squared. So c squared minus 4 has to equal 2c minus 4. So we can add 4 to both sides. And this is quadratic, so don't forget here that you better come up with 2 different answers. So set it to 0 and factor. C could be 0 or C could be equal to 2. Both answers acceptable. All right, so we're getting there here. The definition of continuity at a point requires 3 things. List the conditions, and then let's give an example where it could fail. So the first thing that has to be true, so we could be more formal here and say f of x is continuous at x equals a, if and only if. The first thing that was required is that f of a is defined, or f of a exists. So our counter example for that could be f of x equals square root of x at a equals -3. We know that it's not part of our domain. The second thing that's required is for the left and the right hand limits to give us an overall limit. So as we approach a from the left side, it has to be equal to x approaching a from the right side. So an overall limit will exist. A counterexample for that could be anything that has an infinite discontinuity or a jump discontinuity. So here's one of our typical examples that we've used many times. You could pick any. So this would be at a equals 1. The overall limit does not exist. The left and the right hand limits would not exist, or would not agree rather. The left and the right hand limits each exist, but the overall limit does not exist. And our third case is, does that overall limit equal exactly what we get by direct substitution? So there's no pop point. So our counterexample is when we do have a pop point. So we could have any kind of a function that has a removable discontinuity. So, for example, we could have a piecewise defined function. So if this is the point 1, 2, and this is the point 1, 3, that would be an example where the limit exists at x equals 1, but it is not continuous because f of 1 would be 3, and the limit would be at 2. So that could be a counterexample. All right, it's getting to be a monster video here. Hopefully you're not watching this all in one sitting. All right, so now we need to do our tolerance window for a delta value if we want to use an epsilon value of 0.1. All right, so our graph is a common function. So we know what our graph looks like, and perhaps I'm going to exaggerate. We know it's actually a slow riser. All right, and we want to say what happens at 3. So when x is equal to 3, you can see by direct substitution that our limit here would be equal to 2. And that's why I was trying to exaggerate the growth of that function. And now we wanted to have an epsilon tolerance. So we want to go 1/10 of the unit up. So again, I'm exaggerating my distances here. And as long as you label them clearly, that's fine. So I want to go epsilon units above and epsilon units below. So if epsilon is 1/10, then this line would have the equation y is equal to 2.1. And this would have the equation y is equal to 1.9. And then we want to find these two intersections on our calculator. So this is our tolerance window here. More importantly, we're looking for this delta 1 value. Should make that a little curlier there. And this looks smaller, this delta 2 value. So if we want to stay within that tolerance window, we want to choose the smaller of those two delta values. So we're going to put the equation into our function as y1 into our calculator. And we're going to put in these two horizontal lines. And you're going to find a window that you can zoom into to find these intersections. So I'm going to call this point right here a comma 1.9, and I'm going to call this point right here b comma 2.1. So if we can find the value of a and b, then we can subtract from 3 to find out our value of delta 1 and our value of delta 2. So you could get your problem set up here so that you're ready to find it on your calculator. Remember that you're going to want to experiment with your window so that you have a nice zoomed in view of this. So you know that you want to be close to this point that is at 3 comma 2. So perhaps you might start with an x min to an x max of 2 to 4 and a y min and a y max, maybe just a little bit smaller and a little bit bigger than where your horizontal lines are. So if you use the window settings, that's probably your easiest bet. And I'm going to just transfer the answers from my calculator here. I hope we've seen enough of these now. So let's see, I can come up with the point A, about 2.61. So the distance from 3, that delta value would be about 0.39. And my B value, the intersection on the other side, about 3.41. I'm coming up with those values. I would keep 3 decimal places if my calculator was giving me those values. So how far is that from 3? So that would be a 0.41. So my delta 1 and delta 2 are not equal, and I want to guarantee that I stay within the window, so I am going to let delta be approximately 0.39 to ensure that f of x is an element of our limit 2 minus epsilons. Better to do small value to large value. All right, so to keep our y's within the y range. All right, almost there. If you remember your binomial expansion here, if we just put 0 in for h, you see that we have our 0 over 0 problem. So we've got no choice here but to do some algebra, and that requires binomial expansion. Pascal's triangle gives us our coefficients if we raise this binomial to the 4th power. So it's not difficult, just be careful that you expand your binomial correctly. So our powers on x start out at the maximum, 1x to the 4th, h to the 0, plus 4, x to the 3rd, h to the 1, plus 6, x squared, h squared, plus our next coefficient, 4, x to the 1st, h to the 3rd, plus our coefficient is 1, x to the 0, h to the 4th. And then don't forget, we still have to go back and get that minus x to the 4th, all divided by h. So this positive x to the 4th and that negative x to the 4th cancel. And sure enough, now we can factor an h out of every term of the numerator. And the reason we knew we needed to do that was to solve our 0 over 0 problem. So h is gone, and now we're ready to do our limit. Let h go to 0. So when we let h go to 0, these 3 terms I've just circled all go to 0. So all that remains for our answer is 4x cubed. And that's going to have something to do with derivatives next week.